students, welcome to STEM Renaissance. Today we'll be summarizing Unit 4 and 5 of AB and BC Calc, which is Contextual and Analytic Applications of Differentiation.
First of all, we'll go over two easy and intuitive theorems. The statement of the extreme value theorem is quite trivial. It basically says a function is guaranteed with a maximum and minimum on closed and continuous interval. And the mean value theorem says if a function f is continuous on the closed interval ab and differentiable on the open interval ab, notice this difference, then there exists a point c in the interval ab such that f prime of c is equal to the function's average rate of change over ab. And now for the confusing part. I've seen so many students taking the exam who get confused by this notoriously long and confusing list. However, our main focus is whether f double prime changes sign or not. You can say it's easier to spot a possible point of inflection by setting f double prime equals to 0, but it really won't guarantee you a point of inflection, so you need to make sure the concavity of this function really changes at that point. In fact, since the critical point is when the first derivative is equal to 0, you can easily interpret the point of inflection as finding the critical point of just f prime. I hope this helped you to memorize this list.
Now we're going to derive an extremely famous limit in calculus and in math. First, let y be limit as x approaches 0, 1 plus x raised to the 1 over x power. Now, let's take the natural log of both sides. Now we get the natural log of y equals the limit as x approaches 0, the natural log of 1 plus x raised to the 1 over x power. Recall the property of log. Log a to b equals b log a. Therefore, natural log of y equals the limit as x approaches 0, 1 over x times natural log of 1 plus x. Notice that now we can apply the L'Hopital's rule on the right side of the equation, because the limit as x approaches 0, 1 over x times natural log of 1 plus x equals 0 over 0. Recall that the only two situations that we can use the L'Hopital's rule are when the limit equals 0 over 0 or infinity over infinity. So now we get the natural log of y equals the limit as x approaches 0, the derivative of natural log of 1 plus x, which is the top, over the derivative of x, which is the bottom. So now we get natural log of y equals the limit as x approaches 0, 1 over x over 1, which can be simplified to natural log of y equals 1 over 1 plus 0. So now we get the natural log of y equals 1. Therefore, y equals Euler. So now we can substitute the y variable. We get limit as x approaches 0, 1 plus x to the 1 over x power equals Euler. For this problem, we're trying to find whether the graph of f have a relative minimum, maximum, or neither at the point -2, 8. In order to solve this, first, we need to plug in the point -2, 8 into the differential equation. We get 4 minus 4 equals 0. Now we know the point -2, 8 is a critical point. Notice that we could not use the first derivative test here. When we try to draw the number line of f prime of x, in order to find where does the graph f prime of x changes sign, we could only figure out the value of dy dx at the point -2, 8. We could not figure out the value of dy dx at any other point. That is because we don't know the y-coordinate of any other point. So now, let's use the second derivative test. By taking the derivative of the differential equation, we get 2x minus 1/2 dy dx. Now, by plugging in 0 for dy dx and x equals -2 into the second derivative, we get -4. Since the second derivative is negative, the original function f of x concave down. Therefore, by the second derivative test, the graph f of x has a relative maximum at the point -2, 8. Let's do a problem that involves graph. Again, you can pause this video and try this problem on your own. For part A, we need to find the relative maximum for f of x. First, we could draw a number line of f prime of x to record where the graph of f prime of x is positive and where the graph of f prime of x is negative. By looking at the graph of f prime of x, we get f prime of x is positive from the interval -5 to 3, negative from the interval -3 to 1, positive from the interval 1 to 4, and negative from the interval 4 to 5. Since we know the original function is increasing when f of x is positive and the original function is decreasing when f of x is negative, we can draw in arrows to indicate where the graph is increasing and decreasing. By doing so, we can easily see that f of x has a relative maximum at x equals -3 and another at x equals 4. By using this technique, we could easily find the relative maximum and minimum of any function by looking at their graph. For part B, we need to find the inflection point. Now, we can apply the number line technique again. By looking at the graph of f prime of x, we know that the second derivative is positive from the interval -5 to -4, negative from the interval -4 to -1, positive from -1 to 2, and negative from 2 to 5. Recall that the point of inflection is where the second derivative changes sign. By looking at the number line of the second derivative, we could easily find that the second derivative changes sign at x equals -4, -1, and 2. Therefore, at those values of x, the graph f of x has a point of inflection. Part C. Keep in mind that for part C, we need to find the interval that satisfies two conditions. Okay, so first, positive slope simply means the first derivative is positive. By looking at the graph, the first derivative is positive from the interval -5 to -3 and from the interval 1 to 4. Secondly, we know that a function is concaving up when the second derivative is positive, which also means that the first derivative is increasing. By looking at the graph again, we get the first derivative is increasing from the interval -5 to -4 and from the interval -1 to 2. Therefore, the graph of f concaves up and has a positive slope on the interval from -5 to -4 and from 1 to 2.